Okay, good morning. The last section of chapter 4 is applications of sinusoidal functions and their derivatives. So again, a sinusoidal function, that word, right, is meaning that it's repeating or periodic, right? So we're going to look at a periodic motion occurs in a variety of real world physical situations. So we're talking about, let's say in the past, I'm thinking of grade 11. We had questions about, a Ferris wheel going around, and that created a periodic function, right? Cyclical, or someone in a swing going back and forth. And our equation, I'll move this up as I go here. Our equation of a sinusoidal function is modeled by whether it's a sine curve or a cos curve, same basic equation, right? But we've got here y equals a sine bracket k, t minus d in brackets plus c, or y equals a cos bracket k bracket t minus d bracket plus c. Same equation again, just sine or cos. And again, the period here is the time required for one complete cycle, from the time when the cycle starts to when it ends, and then would repeat itself, because obviously we're talking about just things that are repetitive here, right? So before we go on, let's just kind of address that. I'm going to try to draw this a sketch, but the best I can here. So if I've got, let's talk about, well, any kind of curve here, whether it's a cos curve, change the color. So let's talk about a graph that is starting, let's say here, whether this is a Ferris wheel, let's say, though that doesn't really make sense to go below. But okay, so here is where the function starts. And if we're looking at our cycle or our period, it's going up, maximum, it's coming down, minimum, and then it meets up where the cycle looks like it ends right here. But then I have to take a look and make sure that this part here is exactly the same as this part here. Obviously, drawing wise, it's not perfect, but you get the point I'm trying to make, is that this should be the same, and then coming back down, and then again coming back up. So the cycle starts here and the cycle ends here. So just kind of point that out. This is where a period, or the cycle, right, starts and ends. It's up to you if you want to write this down or not. It might be beneficial, but if you kind of get the gist of it, you may not need to. So our period would be from here to here in terms of, if this was talking about time, right, then that would be our period. And so our period formula is 2 pi over the absolute value of k. And when we look at this example down here, I'll kind of point out again and talk about k in terms of where it is in the equation, but you can see it there until we come back and address it. The frequency is just the reciprocal of the period. So reciprocal is just 1 over the period, right? So what we're really talking about there is how many cycles do I have in a unit of time. So here for frequency, we're talking about a unit of time. So again, we'll address that when we do this example down below, but let's say your question was in seconds, for example. It would talk about 1 second, right, would have, how many cycles would be occurring in 1 second, right, the frequency. And then our amplitude, which you can see our A here is the number out in front before my sine or cos function there. The amplitude is half the distance between the maximum and minimum values. So I don't know if you remember this from grade 11, but we had the equation of the axis, which would basically be exactly in the middle of our maximum and minimum. So if that was, again, if that's supposed to be this, but I didn't do the best job of graphing it here, right? If this was the equation of the axis, right, our amplitude, hopefully you can see this green here, would be the distance from the max to the equation of the axis. It's just halfway, right? Or again, it's supposed to be that from the minimum to the equation of the axis should be the same distance. But again, I didn't do the best job graphing that. And it's the absolute value of A, because amplitude can't be negative. So just what the number is in front, but just the absolute value of that. Okay. So let's jump in and look at an actual example where we're practicing period, frequency, and amplitude. And then we have a part B that's a much longer portion here. So we'll see if we get it all done in one video or if we're going to break it apart here, just depending on length and how long you guys are listening to me. So we've got here the voltage, right? So signal from a standard North American wall socket. So we're talking about when you're plugging something into the wall, right? The voltage that's coming out of the wall is described by this equation. V of t equals 170 sine of 120 pi t, where t is the time in seconds and V is the voltage in volts. So V stands for volts, T is in seconds. So if we compare this, let me just underneath here, just so I'm not going up and down, write out our general equation. So this is a sine curve. So if we had, just going to my pen here, y equals a sine, and I'm trying to write small enough here, of bracket k bracket t minus d bracket bracket plus c. So compare that to this equation. So whatever is in front of the sine is my A. So my A is 170, right? A is the absolute value of 170, which is already 170. So it says the amplitude in volts, and it says right here that V is the voltage in volts, and volts is just simply, here just to write out volts, but V is just, volts, sorry, is just simply a capital V. So 170 volts. I know I skipped down to there, but we might as well, right? Could ask for the amplitude. And then after the sine, so be careful here, I've got a bracket. There's no brackets going on here. So I'm trying to figure out how this compares to my general equation, right? So I've got a bracket K, bracket T minus D plus C. So after the T, I would have a negative or a positive, right? Plus or minus D. Here I don't have, here's my T. I don't have anything after that, and I don't have a plus C. So in front of the T, everything is in front of the T here. So this 120 pi is my K value. So just to point that out here, my K value is 120 pi because that's what's in front of the T. In front of the T is just K, and after the sine and after the sine. So if we're talking about period and we go back up to the beginning here, it said period, just put period equals 2 pi over the absolute value of K. 2 pi is just 2 pi. Absolute value of K is 120 pi. So if I have a pi and a pi here, these can cancel out. And 2 divided by 120, right? If I take divided by 2, divide that by 2, it would just be 1, right, over 60. And my period, my along the x-axis is in seconds, right? So again, what that means is one cycle from the beginning of the cycle, let's just say pertaining to the end of the cycle there, that takes 1/60th of a second, right? Obviously we're talking about voltage coming through the outlet on a wall, that's happening very, very fast, right? So 1/60th of a second is my period. The frequency in hertz. So if we go back up here, the frequency was 1 over the period. So frequency, just going back here, frequency is 1 over the period, or the reciprocal of the period. So 1 over, what's my period? 1/60th. So again, that would be like just going very slow, 1 over 1 times, you change it to times and you flip, right? Flip and multiply, 60 over 1, which that would just equal 60. So what does that mean? So 60 hertz is an HZ, okay, is how you do hertz as a short form. So that means that you have 60 cycles. So you might want to write this down. You have for future questions. That means that, remember we said that that wasn't a unit of time up above for frequency. So my unit of time is 1 second, is in seconds. So in 1 unit of time. So in 1 second, I have 60 cycles happening in a 1 second time frame. So I'm having 60 cycles, 60 periods of these happening in a 1 second time frame. And again, my amplitude was probably the easiest one. I just take the number from out in front, just make sure that it's positive with absolute value there, right? So 170 volts. So this is still relating to the same question and same formula, but we're moving on here to finding the maximum and minimum voltage levels and the times at which they occur. So again, if we're looking at our sine graph, right, we know that it has maxima and minimum values and that it's repeating. So what we're really looking at here is local extrema, just to write down. So how do we find local extrema, right? We need to find our critical numbers for local extrema, and we need to set our derivative equal to 0 in order to get those critical. We've done this many, many times before, right? So get our derivative, set it equal to 0 to get our critical numbers. And then once we have our critical numbers, we'll confirm them doing the second derivative test is where we're headed, okay? To find, so when it's asking for the maximum and minimum voltage levels, again, voltage levels would be like along your y-axis here, right? And the times would be the x-axis at which they occur. So it's asking for, like, let's say the x and y coordinate point there and the x and y coordinate point there is what we're going to end up with. Okay. I'm just going to try to give myself the most room there for you. So to find our critical numbers, let's rewrite our original equation. So V of t equals 170 sine, and their bracket 120 pi t. And again, we know that that was k, but we don't really need to know that for this particular part to get the derivative, right? This is the angle portion. The part in brackets that's after the sine is the angle portion that we're talking about here. This is a constant, right? 170 is a constant. So in terms of getting the derivative, if we know that that's a constant, we're looking at the constant multiple rule mixed with the chain rule here. So the constant multiple rule means to leave the constant alone, the 170, get the derivative of the next part. So the derivative of sine is cos, leave the inside alone, and then get the derivative of the inner, multiplied by the derivative of the inner, with respect to t, because we're talking about time here, right? So that's like an exponent of 1 comes in front, 120 pi, and then it would be t to the exponent of 0, and that would be gone, right? And just to clean this up a little bit here, as I'm setting it equal to 0, I can kind of do both at the same time. I could have just cleaned it up and then set it equal to 0, but I'm just saving myself a line here. I want you guys to see this is a constant as well. So this is going to go ahead and be multiplied by the 170. Okay, so 120 multiplied by 170 is a positive, obviously, 20,000, I'm sorry, 400, 20400, and then the pi. And that's fully a constant number. And then multiplied by my cos of bracket 120 pi t. And my independent variable, right? Like I said, my x-axis, my independent variable is time. This is all a constant out in front. So just to kind of make this a little bit simpler on us, if this is a constant, a derivative being equal to 0 with a constant, the constant would just drop off, right? So really I have 0 and I need the portion that's with respect to time in order to get my critical number. So really 0 is going to be equal to the cos of 120 pi of t, right? Because that's a constant equal to 0, that would drop off. So what we're really saying is, when is the cosine, because we did the derivative, so we're talking about the cos graph here, don't get confused by the original. So we're looking at when is the cosine graph equal to 0? So cos of what, in this portion here, what angle is equal to 0? So then we're going to set this equal to the values of when cos is equal to 0. So I think the easiest thing here would be, let's go look at the cosine graph, and I could draw one out for you, but really this 4.1 note is going to be your friend all throughout here. So if I go here and click here, I hope I can, I'm just going to kind of zoom out a little bit here so I cannot erase what was already there. You guys can see, so first of all, that's the coast graph from the 4.1 note. I've skipped sine, right? And I'm going to the coast graph here. So just to repeat again, zoom out once more. When is my cosine graph that starts at 1, right? Maximum of 1, minimum of -1. It has a cycle of the period is 2 pi, right? Starting at 0, ending at 2 pi, 360 degrees. When is that cosine graph equal to 0? Meaning t, meaning time, which would be the x-axis. When is that equal to 0? So that is equal to 0. We can see here at, just to draw on it, that is equal to 0 at pi over 2, which is 90 degrees, 3 pi over 2, but then this is cyclical, this is repetitive, so what would the next values be? So it's equal to 0 at, you don't write this down, I'll write this down when I get back to our 4.4 note. Now again, if you've ever thought this is pi over 2, so that's like 1 pi over 2, right? This value is 2 pi over 2, but if I have 2 pi over 2, the 2's cancel out, and that's why it's just pi. So 1, 2, 3 pi over 2, right? Then the next value would be 4 pi over 2, but again, 4 divided by 2 is just 2, and that's how we get the 2 pi. So we have 1, 2, 3 pi over 2, 4 pi over 2 is a max, then it would come back down and be 0 here. So at 5 pi over 2, it would also be 0. Right? Then the next value, which would be a minimum, would be 6 pi over 2. Then it would come back up and be 0 again at 7 pi over 2, right? A max at 8 pi over 2, back down to a 0 at 9 pi over 2. So we're just kind of adding 2 every single time. Okay, now we can also look at the left-hand side here, depending on the question. I should be looking at the left-hand side. So we talked about the coast curve, just again, depending on the question, has a maximum of 1, a minimum of -1. The period is 2 pi. But looking at the left-hand side, in this particular question, we're talking about t is time. So time can't be negative. So that's why I'm ignoring the left-hand side. But depending on the question, your values could have equaled also negative pi over 2, negative 3 pi over 2, right? Negative 5 pi over 2, and so on. So just be careful with what the question is pertaining to, and because it's time here and that's negative, then I don't need to include that. So let me erase all this business here. All right, so we figured out, I'm just gonna rewrite that a little bit better for you guys. So we figured out where our coast graph is equal to 0. So this value here, therefore, am I on my pen? No. Therefore, 120 pi of t is equal to 0 at pi over 2 in order, 3 pi over 2, 5 pi over 2, and so on, right? 7 pi over 2, and so on. I would write more than 2. So 3 or probably 4 is probably good, and so on, because it is repetitive, right? So to get my critical number, we're talking about the independent variable t, we need to be isolating for t. So to isolate for t, we would have to divide by 120 pi, right? So divide everything by 120 pi. So here, t would be equal to separating these, right? These are at different moments in time. So we have t equals pi over 2, and just stay with me. It looks ugly, but it's not bad, okay? Just trust me. T equals pi over 2, divide by 120 pi. We're just gonna get it ugly right now. Then 3 pi over 2, divided by 120 pi, right? Beautiful stuff. 5 pi over 2, divided by 120 pi. And then 7 pi over 2, divided by 120 pi. So what? Can we make this look any better? Simplify, yes, we can simplify is what I mean, but how do I make it look any better? So doing this, we would have, again, flip and multiply just like I did with the reciprocal in the A example for, I wanna say, yeah, good, I was right, I wanna say frequency. So we would have pi over 2, right? Flip and multiply, multiplied by, that's over 1, so 1 over 120 pi if you were to flip it, right? So that would be pi on top over 240 pi, so the pi's would cancel out, and I would be left with 1 over 240. Hopefully you can see that. The next one, again, I don't have to write out all the steps after that, like on a test, let's say, if you could go right down to these values, just be careful because I would still have it off to the side not to mess up. So to me, I would still show it. It's always the case, right? The more steps you show, the less likely you're going to make a mistake. So here I would have 3 pi over 2 multiplied by, again, that's over 1. So 1 over 120 pi. The pi's cancel out. And in this case, I have 3 on top now over 240. And then hopefully you'll start to see a pattern. You can't with just 2. You need to continue on. And then 5 pi over 2 multiplied by, that's over 1. So flip it, 1 over 120 pi. My pi's cancel out. I'm left with 5 on top over, still it's always 2 times 120. So 5 over 240. Okay, now I'm starting to possibly see 240 as the denominator, 1, then 2 more, 3, then 2 more, 5. Let's do one more. 7 pi over 2 multiplied by, again, that's over 1. So when you flip it, 1 over 120 pi. Pi's cancel out. Yep, 7 over 240. So that kind of confirms my pattern happening here, right? Now, 3 over 240, let's say, 3 into 24, you can reduce. So I mean, this is the one case where, you know, usually in math, you are wanting to try to simplify and get things down into lowest terms when you can, and you could, but I'm just going to urge you not to. Don't reduce these because I see a pattern here, right? So we don't want to lose that pattern when we're trying to figure out what our answer is. So just leave it in this form when you notice that you have a pattern, because these are our critical numbers, right? So our critical numbers are happening at 1 over 240, 3 over 240, 5 over 240, 7 over 240, and I should put kind of ... because it is repeating on, right? So these critical numbers are endless, like to the right for positive time values, but we need to figure out which one of these are going to be our maximum, which one of these are going to be our minimum values. And so in order to do that, now that we have our critical numbers, we have to do that second derivative test to determine our maxima and minima. So I will just clear this. We will rewrite our derivative. So our derivative function that we already completed in the simplified form, right, was 20,400 pi. And then cos of bracket, the angle was 120 pi t, right? So that's the angle piece there. So again, we have a constant in front. So we have a constant multiple rule with a chain rule to do our, now this is this first derivative, right? So to get our second derivative, right, we leave the constant in front, 20,400 pi. Now the derivative of cos is negative sign, right? So I'm going to put the sign here, but hopefully you'll understand what I'm doing. I'm just trying to change my color here because the derivative of cos is negative sign. Why not put that negative out in front here? So I've got here negative 20,400 pi because it was supposed to be negative sign of the inside, leave it alone, of the inner, and then take the derivative of the inner with respect to t, multiplied, right, is 120 pi. So again, to simplify this, we have here a constant. This is our constant up to pi. We're going to multiply them and put them together. So my second derivative is a negative times by a positive is still going to be negative, but we got a big number here. 20,000 multiplied by 120 pi is 2,448,000, and then pi times by pi. So negative and then pi squared. And then the rest of it sine of 120 pi t. So this might look long, but it's not going to be too bad if you just follow through here. So then the rules would be, the next step would be to plug in our critical number at that second derivative, right? So our critical number for time, the first one was 1 over 240, if you go back. So if I evaluate my second derivative, at a value of 1 over 240 and see, is it a max? Is it a min? What's happening here? So then whenever I see t, right, which is way at the end, so the whole first part just gets copied down. Pi squared, be careful, sign of bracket, what's happening here? 120 pi, a bracket 1 over, did I write that? 1 over 240. Okay, sine of 120 pi divided by. So to clean that up, I can multiply my numerators and denominators together. Just going slow here, showing all my steps. So negative 2,448,000 pi squared, still with my sign, multiplied by sign. Pi's on top, right? So pi is going to stay. But 120 over 240, if you double 12, you get 24, right? So like 120 over 240 is going to go down to a half. Divide by 120, divide by 120. But then I still have the pi on top. So then you've got pi divided by 2. So sine of pi over 2 is sine of 90. That's the same thing as sine of 90 degrees, right? Just for those of you that are more familiar with that. So we're evaluating this at negative 2,448,000 pi squared. What is the value of sine at pi over 2? The sine curve at 90 degrees. So this is where I'm going to go to my handy 4.1. And here's my sine curve. Okay, this is sine of 90, right here, sine of 90. Pi over 2 is a value of 1, you see there. Sine at pi over 2 is 1. So if I go back to here, this whole value, sine of pi over 2, is equal to 1. So it's just being multiplied by 1. So again, this is a constant, right? So if I have pi and I square it, I get a positive number. That positive number multiplied by a large negative number, or just a negative number, it doesn't really matter, is going to be less than 0. Negative 2,448,000 pi squared, right, times 1 is less than 0, which means that I'm concave down. Frown, concave down. So if I'm concave down, then I have a local max at that value. So I have a local max at a time of 1/240th of a second, right? Because time is in seconds. So we have to think, since this is cyclical here, for my sine curve, if I've got a max and then a min, and then a max and then a min, right? And it's repeating. If this is the local max at 1/240th, my next critical number, if you go back, is 3 over 240. So the next critical number, right, should be happening at a minimum. We have to confirm that, but that's what we're expecting, at least, to be thinking ahead. So this is my maxima. Let's confirm that 3 over 240th is a minimum, and then we'll kind of look at a pattern here, right? Then the next value would be a maximum. So just to go ahead, how do I get from this value to this value to this value without having to plug in any more value, just to look at the pattern and say minimum, what would the next minimum be and the next minimum be? So let's confirm the minimum next. So we have our second derivative at 3 over 240 being equal to that expression of negative 2,448,000, 3 zeros, pi squared, multiplied by sine of 120 pi t, and I'm putting in my value of 3/240ths in for t. Negative. It's just a matter of being very neat, right? For those of you that are a little bit messy, please try to keep things neat. There's also less room for error, and I mean, it's going to be hard for me to follow you, right? So try to keep everything neat and tidy and in rows. So sine of 120 pi, and t is a fraction, 3 over 240ths. And again, simplifying, cleaning that up, negative 2,448,000 that should be an 8, sorry, talking and writing at the same time. 448,000 pi squared, sine at, how do I clean that up? So just over here 3 times, so 12, 24, 36, right? So I've got 360 pi over 240. So again, if I were to divide by 12 and divide by 12 there, or divide by 120, I end up with 3 pi over 2, right? 3 over 2 pi, so sine of 3 pi over 2. So then we can go back to the sine curve. What is the value of sine at 3 pi over 2? Hopefully you'll be able to see it. Again, if you have your 4.1, it's going to really help. Sine, right? We're talking about sine at 3 pi over 2 is now -1, right? So if we go back here, that's really, whoops, -2,448,000 pi squared times -1. It's the sign at that value is -1. So again, if I were to think this through here, I have a -1, we did it in red last time, as a constant being multiplied by this negative, which is going to give me a positive number times pi squared. So positive times, that's supposed to be times, positive times another positive. When you're squaring something, the answer is going to be a positive value. So that answer is going to be greater than 0. So greater than 0 is concave up. Smile, which means we did confirm then a local minima at, I have a local minimum at a time of 3 over 2/40ths of a second. Okay, so I've confirmed my maxima and minima. So now let's write out when it's occurring. I don't have the voltage yet, but I know when they're occurring for the maxima and minima values. Okay, so I have the maximum voltages at a time of 1 over 2/40ths, and then 3 over 2/40ths was a minimum, right? So the minimum voltage at a time of 3 over 2/40ths. And then the next one, 5, would go back to the maximum based on the cycle, right? So then I would have 5 over 2/40ths, and then the next one, 7, would be down here, a minimum, right? And then after the minimum, the next one is a maximum, and there are always 2 more. So 9 over 2/40ths, then 11 over 2/40ths, right? And so on. So I have 1, 5, 9, and continuing and continuing. So what's happening here is my denominators are staying the same and my numerators are, if you notice, adding 4. 1 plus 4 is 5, plus 4, 3 plus 4, so that's my pattern, is 7, plus 4, and so on, okay, to continue on. These are my times when it's occurring, but it also asked, if you go back to the question, I'm just find the maxima and minima voltage levels. We don't have the voltage levels yet, and the times at which they occur. We know the times that they occur. So if my maximums are going to occur at 1 over 2/40th, 5 over 2/40th, 9 over 2/40th, and it's cyclical, right? So if these are the maximum values, they're all going to have the same value for voltage. So I might as well use the smallest, simplest fraction, right, to find out my kind of like my Y value here. For the minimum voltages, they occur at 3 over 240, 7 2/40ths, 11 2/40ths. So again, they're all going to occur at the same Y value for voltage. So I'm just going to plug in the smallest, simplest fraction that I have. So to figure out the actual voltage, so to figure out the actual maximum voltage, we're going to plug, that's our original equation, was voltage equation, right? Go back to our original, 170 sine of 120 pi t. And we're going to sub in a value of, for t of 1 over 240. I could have plugged in a value of 5 or 9 over 240, but again, I don't know. Why not use the easier one, right? You could, and you should get the same value. So 170 sine of 120 pi multiplied by 1 over 240. Right, and part of this we've already done. So the 1, that's supposed to be a 2. That's pretty sloppy there. See that? I would think that's a 7 if you did that to me. So just clean it up. It is 170. Oh my gosh. So sorry, my 7s look like a 2 apparently. You know why? Usually I put the line through the 7 for exactly that reason. I'm just writing a little bit smaller here. So for me, yeah, I put the line through the 7 so it doesn't accidentally look like a 2, like what just happened. So 170 sine, and then I go over here to the side if you wanted 120 pi over 240, multiplying my numerators, which again just condenses down to 1 over 2 pi, right? So sine of pi over 2. And we already looked up from before what sine of pi over 2 is. So you can just go look up back up or go back up to your 4.1 graph. Sine at 90 degrees was 1, so I have 170 times 1, so I have 170, and this is representing actual voltage, so 170 volts. So my maximum voltage number would be 170 volts, reoccurring right at different time values. So my maxima would be, for example, 1 2/40ths and 170. At 5 2/40ths and 170, right? At 9 2/40ths and 170. And I'm going to do the same thing here for minimum, just because I have to clear my screen. I don't want to squish it in here, and plugging in a minimum value of 3 2/40ths. And I could have used these values, but I mean, why, right? Why use larger values? So to solve for my minimum voltage, we don't know what it's going to be. We can guess. I want to sub in to my original equation, V at the time of 3 2/40ths. My original equation is 170 sine bracket 120 pi multiplied by 3 2/40ths. Right? So again, we've already done part of that work, 170 sine of, again, off to the side, 3 times 120, right? Divided by 240 ended up going down to 3 pi over 2, and we've already evaluated that. You can go back up and look. Sine at 3 pi over 2 was -1, so I end up with -170 volts. And yes, voltage can be negative. So again, we have values happening because it's cyclical and repeating at a time of 3 2/40ths and -170. And then at the next time at 7 2/40ths and a voltage of 170, and then again at 11 2/40ths, X value known and Y value of -170 volts, for example.